So we're going to start this week, or this lecture in particular, finishing up some of the material that we were covering on Friday, and then we're going to go into this new material, which is going to be actually calculating our K using this thing we call rice tables. And we're going to start with an example that is going to be more familiar to you, and it's going to help you see the logic of using the rice tables. But first, we need to finish up practicing how to write our equilibrium constants. So the first example is barium sulfate in water. So we're just going to throw barium sulfate into a beaker of water, and we want to know what the equilibrium expression is for that action. So first I'm going to write that, and remember how to use a pen. There we go. That our phases matter. So in this case, I have something that is aqueous, an aqueous, and a solid. And if I do it in terms of concentration, I am looking for molar concentration. So that means it's an aqueous solution. That means that my solid isn't going to be included. So when we write our Kc, I'll have Kc equals the concentration of the products over the reactants. And for an elementary equation, the coefficients tell us what exponent goes with each concentration. So I have my barium ion and my sulfate ion, and both of those are raised to the power of 1 because that 1 is inferred with the stoichiometry. So that right there, that's it. I've answered the question for what is my expression for Kc. And the next thing we want to think about is, if you recall in 162 when you did solubility rules, that we said that barium sulfate is insoluble. So keeping that in mind, which one of these options, A, B, C, or D, do you think will best define what our equilibrium constant will look like? You think it's going to be a huge K, a small k, somewhere between the 0.1 and the 100, or you can't tell? So pause and think about it, and then turn the video back on. Okay, so let's see. If it's insoluble, then that means that we're only producing a small amount. And if we look at this expression, just math-wise, if I'm only going to produce a small amount of my products, then that means my K is going to be small. And if I'm insoluble, then I'm expecting K to be really small, because I'm only going to get a teeny tiny amount of those barium and sulfate ions into solution when I put the solid barium sulfate in there. So remember, between 0.01 and 100-ish, we roughly expect the concentrations of the products and reactants to be about the same. A huge K, like a 10 to the 20th or a 10 to the 30th, we would expect most of our reactants to go into products. So we're going to have very little reactant left at the end. In fact, what we see here is our K is indeed tiny, 10 to the negative 10. So considerably smaller than the 0.01 that we came up with, and that tells us that it is only slightly soluble. All right, now I've given you a list of Kcs and temperatures that those Kcs exist at. I want to know, at equilibrium, what do you think the reaction is going to be mostly composed of? Mostly reactants, mostly products, or a mixture of the two? So pause, take a look at each of these reactions, and tell me what you think. Okay, so coming back, we're looking at hydrogen gas and the oxygen gas, the first reaction going into water. And at 298, so roughly room temperature, we have 10 to the 83 is our K. So that is going to be mostly product. We're going to have very little hydrogen and oxygen gas left at the end. Most of it's going to go into water. Then the next one, calcium carbonate, well, we have that teeny tiny K of 10 to the negative 23 at room temperature. If I increase that, say, roughly 4 times to 1200 K, we see that I'm at about 1. So what that tells me is that an increase of a magnitude of about 4 is going to give me an increase of like 10 to the 24th as far as my solubility goes. So remember that 1, that 0.01 to the 100 means we roughly have about the same amount of products and reactants at equilibrium. Then the reaction number 3, let's see, what do we have there? 3.4 at 1000 K. So not a comfortable room, but not exorbitantly hot. What we have here, that means that 3.4 then, I would say we're going to have roughly about a mixture of the products and reactants. It's, again, in that range, so just kind of ballparking. Then the carbon in the water going into carbon monoxide and hydrogen gas. Let's see, what do we have there? That 10 to the negative 21 at 298, so room temperature. That means we're not going to get very much of a reaction there, which is probably a good thing, because if you look at that reaction, that's like writing with your pencil at room temperature. And if I'm writing with a pencil on a piece of paper and I'm producing a flammable gas, that would probably be problematic. Now, if you could take a lighter and like catch the teeny tiny amounts of hydrogen gas that you are emitting as you're writing, it'd be a tricky task, and you're probably more likely to melt your pencil or burn your hand or catch paper on fire before you actually catch some of that hydrogen gas in that flame. So I don't suggest that you try that one out. But again, if we increase that to 1100 K, so now, you know, 3-ish, between 3 and 4-ish times the amount of temperature, now we are getting an equal amount of